Welcome everyone, my name is Yifei Chen. Today I will be presenting my final project for CS358, where I explore CUDA, NVIDIA's parallel computing architecture. CUDA is a foundation for many high-performance applications in fields like deep learning, robotics, and simulation. I will walk through its framework, memory, and hardware architecture, API key advantage, and real-world use case. By the end of this talk, I hope you will have a clear high-level understanding of what CUDA is, how it works under the hood, and why it continues to dominate GPU programming. Let me begin by introducing CUDA, which stands for Compute Unified Device Architecture. It's a parallel computing platform and programming model developed by NVIDIA starting in 2007, and it has since become the industrial standard for programming on GPUs. Unlike traditional GPUs that were originally designed only for rendering graphics, CUDA allows us to harness the tremendous parallel computational power of GPUs by general purpose tasks. This is often called GPUs, or general purpose computing on graphic process units. This shift has been transformative across many domains. CUDA is now the backbone behind deep learning frameworks like TensorFlow and PyTorch, powering massive neural network training. It's also widely used in robotics, where real-time vision and control systems require fast parallel processing. And in scientific computing, CUDA accelerates simulation in physics, bioinformation, and computational finance. In short, CUDA dominate access to GPU computing and build an ecosystem where developers can write highly parallel code efficiently, with deep integration into modern toolchain and scientific workflow. So this chart is I borrow from the class notes, representing a spectrum of programming difficulty in parallel computing, from manual and low-level control on the left to the high-level automatic parallelism on the right. CUDA here is positioned here is a better language for GPU programming. It offers a low-level control like MPI, but within a structured model. CUDA combines high performance with developer-friendly API, and it supports other modern language like Python, Rust, through bindings. From this spectrum, we can see that CUDA balance power and programmability. It's more difficult than using NumPy, but far easier and more productive than MPI or raw GPU assembly. For developers who want to control and performance on NVIDIA GPUs, CUDA hits a sweet spot. In CUDA, we program using a hierarchy model of parallelism that mirrors GPU's architecture. At the core of this model is a kernel, a function that is executed in parallel by many threads. Threads are grouped into blocks, and blocks are organized into grid. Each thread performs the same code on different data. To identify their position in the hierarchy, CUDA provides built-in variables. So thread IDX gives the thread's index with a block. Block IDX IDs gives the block's index in the grid, and block dimension describes the size of the block. Using this, each thread can calculate its global index. That this lets split a large task like processing a matrix into small pieces that each thread can handle independently. This diagram shows that structure in 2D. Each blue square is a thread block, and each orange square is a thread inside a block. This layout is great for parallelizing image or matrix computations. More importantly, threads in the same block can communicate share memory and synchronization using synchronized threads, this kind of functions. But threads in different blocks cannot directly synchronize during the execution process. This model is scalable and flexible, and is one of the CUDA's biggest strengths. The CUDA hardware architecture is engineered for parallelism. At the core of this design are streaming multiprocessors, which are also called SMs. Each contains numerous cores, wrap schedulers, and one chip share memories. These streaming multiprocessors operate independently, handling different thread block and scheduling wraps. Each wrap, a group of 32 threads, is a fundamental unit of execution. SMs selects which wraps to execute at each clock cycle, enabling high throughput. This design allows one wrap to complete while another waits for data, a process called zero overhead context switching. This massively parallel architecture is why GPU can handle large-scale computation, like matrix operations or physics simulation, far more efficiently than the only CPUs. So for the CUDA memory hierarchy, CUDA organizes memory into several levels, each with different speed and visibility, which we also kind of learn from the class. At the top are registers, the fastest memory used by individual threads for local computation. Next is shared memory, which is on chip and shared among threads in the same block. This is ideal for cooperation and data reuse. For example, tuning in matrix multiplication. Uh, Global memory is large and accessible to all threads, but much more slower. Access patterns like classing and are important to reduce memory bottlenecks. Constant and texture memory are both read-only and cached. Constant memory is great for broadcasting small values, and texture memory is optimized for 2D spatial access. Finally, unified memory abstract away the boundary between CPU and GPU memory. Is convenient, but many may introduce overhead from automatic transfers. In the diagram, we see how each thread accesses its own local memory and registers, while shared memory and global memory are visible to broader scopes. Choosing the right memory level is key to writing efficient code and programs, which also mentioned in class, very important for different kind of parallel coding codings. CUDA provides both runtime APIs and a driver API. The runtime API is widely used with functions like CUDA malloc, CUDA memory copy, and kernel launch syntax. It simplifies GPU programming by hiding low-level details. The driver API offers fine-grained control over context and memory, but is more complex and typically used in advanced or multi-GPU scenarios. Beyond its APIs, CUDA's real strength lies in its optimized libraries, like CU BLAS for fast linear algebra or CUDN for deep learning layers used in frameworks like PyTorch, and other like CUFFT, Thrust, NPP for signal processing, C++ program algorithm, and image operations. This library let developers achieve high performance without writing every kernel from the scratch. Here's a simple CUDA program that adds two arrays elements wise on the GPU. At the top, we define a kernel function called add. It runs in parallel. Each thread handles one index I of the array and performs one addition. In the main, we use CUDA malloc to allocate memory for the three arrays A, B, and C on the GPU device. Then we launch the kernel using the syntax that means the one block with n threads. Each thread executes the kernel independently. Finally, CUDA memory copy is used to copy the result back the GPU to the CPU after computation. This example shows the basic CUDA workflow. It's allocate memory, launch parallel work, and transfer data back. A pattern you will see most in CUDA programs, and we can also see this a lot in like using MPIs. So for the strength of the CUDA, its key advantage lies in its ability to extract maximum performance from NVIDIA GPUs. Developers can fine-tune memory access pattern and the thread behavior to achieve near-peak hardware performance, crucial for scientific and AI workloads. Its intensive library support, including what we mentioned about the CUDN or CU Plus and others, enables rapid development without need to write low-level kernel code. These libraries are highly optimized and maintained by NVIDIA. Furthermore, CUDA offers mature debugging and profiling tools such as Insight System and Insight Compute, empowering developers to diagnose the bottlenecks and tune performance effectively. Combined with a large active community and extensive online documents, CUDA provides one of the richest ecosystems in GPU computing. Okay, but there's definitely some limitation of the CUDA. Despite its range, the most notable is that it is vendor specific, designed especially for the NVIDIA GPUs. This restricts the portability and ties software to NVIDIA's ecosystem. The programming model also presents a steep learning curve. Developers must deeply understand memory hierarchies, thread execution models, and performance tuning techniques to write efficiently code. Even small missteps can drastically impact the performance. Debugging current code remains challenging. Race conditions, rapid divergence, and bank conflicts are common issues that can be hard to trace. Moreover, transferring data between the host and GPU memory over PCIe introduce bottlenecks, particularly when large datasets are involved. This is very painful when doing some kind of simulation because you have to trace back to the bottom computation. CUDA's application is very rich, so they use across a huge range of application. In deep learning, it powers model training and interface in framework like PyTorch. Robotics relies on CUDA for visual SLAMs and perception. Graphics and simulation tasks like path tracing or real-time physics use CUDA for realism and speed. In science, molecular dynamics and computational finance use CUDA to simulate and optimize massive systems. CUDA is general-purpose engine wherever parallelism matters, but it will only use NVIDIA's GPUs. And here's a table compares CUDA to other major framework based on four aspects. CUDA delivers the best performance and strongest ecosystem, but only on NVIDIA hardware. It's low level but highly optimized. OpenCL and CYCL are more portable across vendors. CYCL offers more than C++ abstractions, when OpenCL is more low level but less widely adopted. And also OpenMP is CPU focused on with some GPU support. It's easy to be used. We already see it in our assignment and class, but doesn't offer full control of performance on GPUs. It's not hardware specific. Also, MPI is for distributed computing, not for GPU centric, but essentially in supercomputing clusters. So in short, CUDA is the best if you're targeting NVIDIA's GPUs and care about performance. But for portability or hybrid CPU and GPU systems, other tools may fit better, but we still consider the performance specifically to the problem we want to solve. So to summarize, CUDA is a powerful, well-established platform for GPU computing, especially on NVIDIA hardware. It's ideal for tasks that demand high performance, like deep learning, robotics, and simulation. It comes with rich ecosystem for libraries and tools, and there's plenty of documents and community support to get started. Although it's very hard, it have a very hard learning curve. And if you and everyone wants to learn more about it, I recommend checking out the official CUDA document, the NVIDIA developed port, and also one of the textbook called Programming Massively Parallel Processor by David Crick. And finally, here are some of my reference for doing this kind of overview of CUDA language. Thank you so much for listening.